this meeting. Today, I will be talking about the research that we began in 2016, working with our colleagues in material science and some folks in the data science and machine learning group at Texas A&M. And we've been constantly working on some aspects of it. We got some funded projects in this, like 3 or 4 in this time. But what I will be presenting is more from a manufacturing standpoint as to what kind of challenges are there, and then what kind of problems that we have been able to tackle and what kind of outcomes we've been able to get. The remainder of this talk will try to follow this type of an outline. I'll try to introduce this autonomous materials discovery and manufacturing in the way that we have been looking at it and provide the necessary background as to what exists. Then I will drill into some of the developments that we have been able to be part of at Texas A&M, developing a hardware platform, which we call as the Smart Hybrid Machine Tool, on which we are kind of building this autonomous discovery system. And also look at some of the AI/ML methods that help with rapid characterization, which may be of interest to many of us here. At the outset, why we need to do autonomous materials discovery and manufacture. In fact, as time progresses, the need for such discovery is going to only grow. With the impetus towards sustainability, newer kinds of materials for batteries, especially from a strategic standpoint, security demands newer materials for our defense and space systems. Think about hypersonics and other kinds of things. And also with ultra-high energy platforms like nuclear reactors. And I'm sure you must have heard about this breakthrough at Lawrence Livermore in fusion reaction. So the kinds of material systems needed are some things that go beyond what are in common use today. In fact, people need to come up with newer kinds of materials. And this need for materials is only growing because of some of these socio-political scenario that we are seeing for making sure the available materials can be modified and newer kinds of material systems discovered to effectively meet the emerging realignment of supply chains. Okay, so the growing push for better materials with desired properties. For example, in different systems, you basically need different kinds of properties. For example, battery systems, you probably need high energy density, thermal stability with low self-discharge rate. These are the properties you need to target towards. And for defense applications, for example, hypersonic material structures, there you're looking at a different combination of properties. And the suitability of material depends on how well they can deliver those properties, right? But it's not so simple. It's not just about thinking up the materials, but you need to actually make them. The story I can probably bring based on the case study of one of my colleagues, Ibrahim Karama. A few years ago, he was able to deploy the material he discovered into an aircraft system. It's a torque tube made out of shape memory alloy. But if you think about what it actually takes to actually make those components, you actually have to come up with the right combination and make the material undergo elaborate process chain of vacuum melting, forging, and then rolling, and then final heat treatment before you have a semblance of material that you could work with. Right? And each step of this process chain, you have to precisely control the composition, temperatures, as well as the processing trajectory. It's almost like making an elaborate and complicated recipe that you can eat, right? So you basically need to clearly make things, right? Those of us who make things, salt is an important ingredient. In here, shape memory alloys, some of these trace materials are extremely important ingredients. Even a fraction of a percentage difference can make a difference between whether you're getting that shape memory effect versus not. And so as a result, the whole thing took multiple years. It actually took 15 years from the point where Ibrahim thought about this material till he was able to actually see the material function the way it was intended to. What was happening during this time? It's all literally Edisonian approach. That's what the material scientists do. Trial and error, right? I'm sure those of you who are actually working in materials can quickly relate to that. You kind of build a nice process to make this material. What comes out is literally junk, right? And then a couple of more iterations, you try to improve, and suddenly the eureka moment happens, right? And you get to what you're looking for. This trial and error is extremely elaborate, time consuming, and then extremely resource intensive, especially in materials and manufacturing domain. The experiments that we really think about can run into a few $1,000s for a single run. And you basically need to make sure not only you're making them, but you're studying what you have produced so that you can actually see if it actually meets what you're looking for or how well it does. Right? So that type of a discovery process as it stands today is highly inefficient. And this is pretty much is a legacy from centuries of discovery process. But now we have a newer challenge in hand. The idea is, can we think about this entire discovery process into some sort of an abstract frame and see if we can create our computers to do this discovery for us? And if so, to what extent they can do, right? So just to abstract things up, every experiment in effect is basically a point in this materials design space. So you're trying to create a particular composition, what kind of elemental compositions you need to have for that particular alloy or particular type of a material, and what kind of a recipe, and what kind of a process chain, and what kind of conditions you want to have so that you can get that particular material made. So that process is essentially one of traversing this highly high dimensional and complex materials design space, where each point happens to be one experiment. And based on that experimental trial, you will kind of use your intuition to tell where your next trial has to be and kind of traverse through this. And then that's what took Ibrahim 15 years to kind of come up with. So taking one experiment at a time. So one combination of composition and then one type of setting for all these different process parameters. Of course, it's too long, expensive, and of course, it needs to be improved. And autonomous materials discovery and manufacturing focuses exactly on this challenge. And we are not the only group looking at this autonomous materials discovery. In fact, Department of Energy calls this autonomous materials discovery as a grand challenge of today and uses this phrase on very few things, and this happens to be one of those. But even greater a challenge that we are trying to look at is the fact that you can think up and you can make a small piece of that material, especially in the polymeric. You can actually create a good polymer that has certain functionality at microscales. Can you create and can you actually manufacture at bulk scales these types of materials? And let's think about a way in which you can autonomously discover and make these materials for engineering applications in a single or basically a single laboratory or a shop floor platform. That remains the major challenge of autonomous materials discovery and manufacturing. So to state it, the objective of this whole AMDM is to discover novel materials with specified tailored properties, plus their manufacturing recipes or the process plan, all done by the computers using AI and data science. That is basically the major objective of this work. And when we think about autonomy, that is another one of those abused words that you get to see, right? So I can put autonomy so that I can get funded, I guess, right? So, but autonomy, essentially, if you go into the roots of it, it has to have two components. An autonomous system has to have ability to learn. In the case of AMDM, it needs to have the ability to learn the underlying relationship that connects the process with the material that you made and the property you endow in it, PSP, right? And second is adaptation. You are not only learning about this relationship, but You are trying to sense what you are able to see of the current state of itself and the environment. And based on that, you kind of tune your next step of how you are traversing the next step of your discovery process, be it in terms of changing the settings for the next iteration of your experiment, or changing the process settings on the go based on the parameters that you are able to glean. So that type of learning and adaptation are essential components that you need to have or any kind of an autonomous system. And of course, you can go into the next higher levels of autonomy. The system can have the ability to have cognition, have empathy, and ability to be surprised and react to the surprises, and have higher order reasoning just beyond what it's able to learn. Okay, and an autonomous system in this context has to be thought in terms of and framed in terms of these properties that we want to enter. Okay. And how can we build an autonomous system for materials discovery and manufacturing? We can think in terms of an autonomous cyber physical system that we can construct for AMDM. In effect, such a system will have two components. The first one is the one that you see on the top, a brain. And it basically uses some kind of AI built into it. And second is basically the brawn or the body of that system, which is essentially the manufacturing shop floor. So essentially, in some ways, an AI-driven manufacturing floor is what you can think about. And there is always a debate, which is not well settled, as to whether an autonomous system has to be automated, essentially, or can an autonomous system be without full automation, right? So they are complementary, or they basically subsets of each other. Is something that's debatable. But in essence, an autonomous system has to have the properties that I mentioned. And also, it needs to address some interesting challenges here. The first one is it has to be able to learn the process structure property map that I had alluded to earlier. And it needs to be able to learn from the data that emerges in the process of the discovery and adapt itself. And what kind of timescales over which these data appears, and over what type of spatial distribution these data emerges, those need to be considered too. And also same thing with the adaptation in terms of how it adapts and how it reacts to those, right? And in this context, it's important to discern and decipher the difference between process to structure relationship and structure to property relationship. If you look at the overall material science work in this autonomous materials discovery in particular, or materials design in general, the focus remains almost exclusively on capturing this structure to property relationship. So given my structure, what kind of properties would I have? Very little has focused on, at least relatively little, has focused on connecting the process to the structure. If you look at even the best papers produced in this regime, basically simplify the process to some static process parameters. Right? So basically, they assume that if I put that particular laser power for my 3D printer, or a particular speed, feed, depth of cut combination for my CNC, I'm going to get the structure that I want. That's an oversimplification, right? So you need to clearly understand how the process as a dynamic entity informs the structure. Second aspect, second challenge that I had alluded to, but let me repeat, is the bulk scale synthesis. You can always concoct a material on your computer. And you can also, if you are lucky, you can always build a material at nano and micro scales. Trying to build several millimeters or even like foot-long dimensions for these materials becomes a challenge. Because you need to control not just the microstructure, as the material scientists would like to focus on, but go beyond that. You need to control the morphology, composition, and the geometry of the material. How can you endow those? Third important challenge emerges from our ability to react to what you perceive. These control loops can happen at three different scales of resolution. You can control the process chain in the sense that go from one machine to the other. I can skip one machine and so on. Just change the process flow. Sometimes you might need some extra rework. You can build that. So essentially creating that process chain sequence control. Second aspect is looking at an equipment, trying to change the settings of the equipment. And third, which is probably more important for materials discovery, is the process state control. How can you control the state of the process or the state of the materials that are being made as they are being made? And also, while you do that, you need to think about a way in which you iterate across the experiments from what you learn and how you react by intelligently traversing in the space of the materials that I spoke about, the high dimensional space. Whether you kind of see some good opportunity and then search around that point to get the best result, or look at a point that is far away opportunistically for looking at something like fool's gold, I guess. So yeah, there may be something out there. So how do you kind of go search for this gold mine of the new material that you want to discover? These remain the essential challenges. So if you want to actually develop a system that achieves this autonomous materials discovery and manufacturing, you need to have a way to address these challenges at the very minimum. And one implementation that we have got going at Texas A&M, we call it the Smart Hybrid Machine Tool Platform. The remainder of the talk, I'll just basically share with you what this platform looks like and how we are kind of using, or what we are using this platform for. Okay. This, if you can think about a hybrid platform as something that puts together multiple manufacturing processes into a single machine tool. So I like to call this as Swiss knife for manufacturing. So you can think about this machine. You can 3D print using a particular type of a 3D printing process. It's a laser directed energy deposition. And you can actually have a CNC head just next to it. Actually, I don't know whether you can see it well. There are two things. On the left, you see a laser head. On the right, you see a CNC head. So you can actually use different kinds of machining. End milling works really well. In addition to that, you can use the same laser heat to kind of upblade the surface and beyond. And also, this machine has a turret. Basically, you can actually have 8 to 16 different tools with which you can work on the surface. You can grind it, you can form it, you can polish it, and so on, right? So the advantage to putting all of them into a single machine is dating. Whenever you want to achieve precision, datum is important, right? And you can actually tee off of what you printed to kind of ensure what you subsequently machine meets what you want, right? Reduces the processing time. And also, since you're actually looking at multiple processes in a single location, you can possibly achieve better control, not just over the geometry, but also morphology and possibly microstructure. And you can actually get some energy efficient process chains because the material gets a lot of energy into it during the printing process. How can we really harness that energy so that you can probably process that material using much more favorable regime during machining and so on, right? So these are all some kind of possibilities. I'm going to kind of see if I can play the small video here that shows that machine and how it's actually works. So essentially you have a laser head.
The Smart Hybrid Machine combines additive manufacturing and machining. It uses lasers, metal powders, and heat treatment to modify the structure and properties of the created materials while collecting data about the material. This process can be automatically controlled using a computer. The computer uses code to create parts that can be simulated and verified by the machine before printing begins. The synchronous use of a high-speed camera and other instruments allows for faster data collection, which will speed up the discoveries of material properties. Around 1 gigabyte of data is generated every minute by the machine. This data, along with the discoveries from the machine, are speeding up materials discovery for the future.
Yeah, and just let me break this down a little bit. this machine actually can produce multiple batches. Within each batch, you can possibly create maybe, I would say, like centimeter footprint, centimeter by centimeter footprint, a dozen such materials. Each material can be made of totally different materials. Each structure can be made out of different materials because you have a combination to do instant alloying. In fact, each layer of this material each layer of this structure can be made out of different materials. Here you can see that the bottom has a slightly different materials on top. So one was 316L, the other one is cobalt chrome. You can just put one on top of each other. And in fact, each layer can be a different alloy in itself, right? And each track can be different ones too. So you can actually enhance the process chains. You can have multiple materials. You can synthesize in a single build. You can have thousands of different materials, and you can basically adapt it based on what you see of one material to build the next material and so on, right? And we have been building some kind of external control loops to enable the use of information that we glean from various sensors to be able to adjust these so-called G codes on the fly, right? And you can have this process chains not just limited to 3D printing alone and machining alone, but combinations actually create some very interesting synergies. And we have dabbled with different kinds of metallic materials. But most importantly, we can actually create characterization ready samples while you're building it. So in other words, we pretty much literally start with clean slate, or basically clean plate. And we can 3D print and then use this process chain to create surfaces that are almost like metallic mirrors. You can actually etch it, or you can actually image it. You can do lots of interesting things. The same thing, right? So we can, of course, it's all students who did all the hard work. They actually can demonstrate that they can get RAs as low as 10 nanometers, right? And possibly over time, they can do even better. And more importantly, this machine has been endowed with 14 different channels of sensors. We call this magic plate. So under the substrate on which you build the thing, we basically built a lot of MEMS sensors, thin film sensors to measure forces, acoustic emission, vibrations, and so on, right? In addition to having these images to capture what's going on. And then we have been able to use some of the process knowledge itself to be able to align them to a few millisecond precisions and a few micrometer precisions in space, right? So on the left-hand side, you see multiple data streams synced up. And on this side, you see acoustic emission, accelerometer, forces, and so on, thermal images, and the data from the controller itself, OPC data. All of them could be captured, not only for printing, but also for machining. From a research standpoint, what's exciting here is our ability to monitor the process in ways that are very, very unique. While you're building a particular part, you can possibly go to observe a particular small voxel, I would say a fraction of a millimeter by millimeter voxel on anything that you printed, and then go back and ask, what was the signals that were generated while that particular voxel was being printed and subsequently being machined at a different time, right? Or you can go back and look at the surface and then see what was happening to the process. Are there some interesting things that was happening during the process? So essentially, you can actually do what is called multimodal data analysis and interesting interrogations that are actually going to be very important for autonomous materials discovery, because that's the data that you need to have to enhance the perception to be able to adapt effectively. Right? So this type of alignment actually builds us some very interesting possibilities. So that's where I'm going to talk the remainder of this time on some of the interesting AI ML methods that we were able to do. Specifically, we're not looking at improving the way we make the part, but we are looking at the way we actually measure what comes out of the process. Right? So we call this rapid characterization. Why do we need this rapid characterization? Because when you look at these materials that we are using for materials discovery, we fabricate, and then once they are fabricated, you actually remove the samples many a times. And for each, before you kind of finish it, you level machine, rough grind, then you hold the sample in some kind of a polymer, and then you polish, and then you do microscopy and other kinds of analysis, right? That's usual process chain for studying and assessing the properties. And typically it takes not just many machines and many steps, extremely time consuming, and need multiple experts to be able to do. Quickly, you can see why this hybrid machine can solve some of these problems, right? You can do all of these things in a single setting, right? As we mentioned, we can actually go through these things and then improve the surface as we are actually making it within a matter of a few minutes, right? Print and all the way to polishing can be done very, very rapidly, right? And more importantly, the signals that we are getting can be used for interesting characterization applications, right? I will kind of accelerate a little bit so we can actually go through this in less than 3 hours from the moment you decide to print a particular material till when you have all the property information, or then some of the important property information on you, right? How do we do that, right? The idea here is to look at how the process informs the microstructure or the complete structure, and then how it in turn informs the property. And when we look at the whole cycle here, the last AMDM conference, it's called DMDI conference that was done by National Academy in November of 2022, basically kind of honed in on this issue of structure. You can make the parts, you can measure the property, but getting the structure measured, characterizing the structure remains the important bottom. And when you talk about structure, we should not just be myopic and just look at the microstructure or combination. A structure is essentially a multi-scale entity. You need to look at the geometry, morphology, microstructure, and composition. In the remainder of this talk, I'll just talk about one example of how we use to study one aspect of morphology and one aspect of microstructure and properties. Right? When we talk about morphology, of course, in addition to the surface roughness, you have to worry about some of the interesting traces a process leaves behind. For example, in the 3D printing process, ripple structure is an important determinant. Pretty much, once you capture the ripple structure effectively, you can pretty much tell what kind of microstructure and then the grain structure you get to see. And also, you need to worry about some of these interesting features, sometimes called defects, like surface pores and voids, internal inclusions, scratches, and other kinds of external features that you get to see. And these basically tend to kind of seriously undermine, oftentimes, the properties that you're looking for. It's not the microstructure, but it's actually the issues with the morphology that you need to really be able to account for. And the research has effectively focused on many of these, but most importantly, it studied the surface pores and prediction of these pores in 3D printing process, because pores tend to be extremely deleterious. People have also talked about effectively controlling the pores so that you get the right kind of effective density for some applications. But nonetheless, pores can be a major issue, and you need to be able to effectively monitor and track these pores as the process goes. And these are some of the things. It's an eye chart here. Most of the prior works use different kinds of imaging techniques, where you put an expensive sensors onto the printer to be able to monitor and then use the data from the sensors, whether it is like high-speed camera or thermal camera, and use those thermal history or the image history to be able to predict. Some of these tend to be extremely expensive. You cannot just translate any of these. And also there are some issues there too. Second aspect is there's some people have tried to use acoustic emission signals to be able to predict. So essentially they are kind of looking at the acoustic emission energy to be able to predict whether that particular part will have or will not have a pore. But they were not able to localize whether a particular region or particular voxel within a particular part you're going to make, whether it will have pores, or if so, how much, and so on, right? So there is no specificity. So what we try to do is, can we actually predict whether a particular voxel here, particular voxel that you have printed, whether it's going to have or not have pores based on the various stacks of data that we were collecting during the process. So we are collecting acoustic emission, all that, right? If we think about this as some kind of a data stream, can we use that data to be able to predict whether that particular voxel has pores or does not have pores? And we can think about each voxel to be of the order of 1 millimeter or less, right? So in other words, can we go as if sprinting, look at every 1 millimeter area based on the signal, how well can we predict? It turns out, if you're just using the printing data alone, you can get fairly good prediction accuracies, right? Prediction accuracies can be, for training, of course, you can get quite high, but even for testing, you can get at least 70%, right? So there is a high correlation between some of this data that you collect. You don't have to use high cost images, simple cheap data, simple MEMS sensors, literally less than $10 each can be used for some of these applications. Of course, great. Deep learning can relate anything that you want, right? But is there any physics underlying it? Is there something that we can learn about the process? So that's where we actually use some methods called explainable AI or XAI to look deeper into why this happens. How much time do I have? Can I have?
Well,
3 minutes?
Including question and answers, 15 minutes.
Okay, I'll try to wrap it in next 5 minutes. That will be good. And so what I will do is, like, I'll give you an intuitive idea of what this is, right? And then based on that, we can drill deep into some of this. Okay, okay, good. Again, I'll keep it intuitive as opposed to getting into the depth. Okay. Essentially, if you look at any kind of these big deep learning models, it connects any input to the output, but the underlying functional form is extremely complicated. Of course, you can see that functional form, but you will not be able to tell why this relationship turned out to be very important. Or for example, if I have a particular relationship connecting my spectrum to the presence or absence of defect, or probability of a defect here. Why did this particular pixel on my input image contributed to informing the porosity? We will not be able to discern it. And trying to come up with which of these frequency features or which of the features in the signals that I'm collecting is important is actually a bad question to ask. Because at different regions of your input space, you will have different type of a relationship connecting your input to the output. This, a simple line graph illustrates it, right? Suppose I'm looking at a particular pixel here, or a particular acoustic emission data. As my acoustic emission increases in terms of its intensity, the probability of presence or absence of a pore does not increase linearly, but it increases and decreases in a very nonlinear way, right? As you can see here, around this value of intensity, as intensity increases, the probability drops. Whereas in here, around this point, if the intensity increases, the probability increases. But if I take a global picture, if I look at a particular component, how it influences, it's almost like putting one foot in the cold water, other one foot in the hot water, and saying that nothing influences. So you get highly misleading results. So what these XAI methods do is they basically look at coming up with simpler explanations for every region and stitching them together to derive some global explanation. Okay. And they use simple linear models around each input to come up with some sort of a beta. Beta basically tells you the influence of each input component on your output at a particular location. And based on that, it generates multiple betas, one at each location. And based on the beta values, collection of beta values, it basically provides an idea of how your individual components of data inform your output. And you can actually learn something very, very useful from there. And it actually uses some kind of perturbations of your input image and creates a samples to build these types of models. And here you need to be extremely careful about how you choose these perturbations. Otherwise, you might get some kind of absurd results. So there are some very nice works that are happening in terms of building the right kind of models to generate these local explanations. And once you build those local explanations, how do you bring them together to create the global understanding, stitching them together? That also remains a major problem. And there are also different kinds of ranking criteria that people have developed to consolidate these local inputs to create a more stitched up response. And even more important challenge here is, based on these outputs, how can you generate the physically meaningful information about what relationship you're trying to track? How do you come up with a physical explanation from purely the mathematical outputs from these line models? So to illustrate that, we kind of show the simple result that we got. For this particular model, we found that the line importance, the beta values were very, very high for the high frequency components of the acoustic emission. So in other words, nothing else mattered except for these high frequency components here. And it somehow shows that for non-porous voxels, you have slightly higher energy compared to the porous voxels, right? For these higher frequency components. That's great, right? Why do they happen? So it turns out that if you look at these higher frequency components of acoustic emission, at different points in time, these higher frequency components have different levels of energy. It's almost like some kind of a waveform was taking place, right? And the variations for the non-porous were much less compared to the porous voxels. That's first thing. So as a result, for porous voxels, you're kind of on-off behavior, and as a result, the energy was a little bit low. Second thing that really stood out was that even among the porous voxels, you have this whole region is split into two. When you go back and observe the images, you basically have higher energy among the porous voxels when you have spatter, which I'm going to show in a minute, versus when you don't have spatter. So in other words, some of the, I'm going to skip this in the interest of time. I'm going to show this. Whenever you have slightly higher energy among the porous voxels, you tend to have highly spattery patterns in your thermal images. So you have a lot of these things that are kind of almost like sparklers flying on the July 4th, right? And when you don't have that low energy in the porous voxels, you basically have very benign type of approach. So you basically have this huge energy variation. And if you look at the overall results once again, the higher frequency band of acoustic emission pretty much carries the information needed for detecting pores, pores within a particular voxel region. And this high frequency bands are somehow capturing the information related to the spatters that are taking place. And we are still working a little bit on how we can clearly characterize the time frequency characteristics of the acoustic emission to the generation of spatter. And there may be some very interesting outcomes that we are looking for, where we can actually use it to effectively control some of these pore formation mechanisms. And I'm going to shift gears a little bit, and I'm going to just run through an interesting facet of what we have been doing. We can also use not just the acoustic emission, but simple images that are taken online or offline to determine some of the properties. For example, you have this microstructure with a diamond here, where we actually put a dent into the surface, and this dent was put on a micro hardness tester. When you put a dent here, it gives you some kind of an assessment of the hardness. Okay. So the question that we are looking at is, can we look at this image and be able to predict the hardness of that particular region? Why is this important? Because to go and then get that measurement offline will take an hour. Can we actually have this thing, have the surface, and then use those images which are abundant to be able to predict out what kind of hardness it has. But you need to, if you look at the surface, it's basically highly heterogeneous. It has different kinds of grains, and then you have different grain boundaries separating them and so on, right? So what you measure as hardness is basically a result of the composition of different kinds of grains putting together, right? In some ways, predicting this hardness is very similar to predicting how the face of my child will look like by taking a photograph of me, right? But you can do a little bit better if you can take not only my photograph, but my wife's photographs and maybe the photographs of all my relatives. And then if you put together and if you put it into a machine learning method, may be able to have a better chance of predicting the photograph of my son, right? Something like that, right? So that's what exactly we did. Instead of trying to take the photograph exactly here and then use that image to predict, we took the nearby surrounding images. And then we built a foundation AI-based methods. So essentially, we trained a VGG16 for feature extraction. Basically, it compresses this tensor into some kind of a flattened, low-dimensional representation, and use this low-dimensional representation to be able to predict the hardness. In our case, we were able to predict. I'm going to run through this very quickly in the interest of time. That's exactly what we have done. So we just looked at the region of interest. How do you determine this? And within the region of interest, we can select multiple inputs. And from multiple inputs, you basically need to recognize the diversity of pattern you're getting, right? You get different mixtures of grains, different kinds of textures, directionality, the grain boundaries, all kinds of different features you can get. And you use these 10 images somehow captures a combination of all those, and then send it through a kind of foundational AI model. I'll kind of skip the details of this. And once you do this, we are actually not just getting the features, but the features were revealing something very, very interesting. So at different layers, different kinds of information is captured of this thing. You can go look at these grain concentrations are captured in different layers. The mixtures are captured in some other layers. The orientations in some others, and grain, I mean, everything somehow captured in this this deep learner that we were able to leverage. And from this, if you just use a simple relationship, basically a simple model connecting this feature to the hardness, you can get really, really good representation. Again, why it works is basically we believe it has something to do with taking the information of all my family and relatives to be able to make that prediction, right? So what is the advantage from a practical standpoint? If these kinds of approaches work, you don't have to take the part to the micro hardness tester, right? While you're making, you take a picture, and based on the pictures, you can hope to get some of this information. Of course, that particular micrograph should be properly done, right? There are other kinds of things that we can do, but in the interest of time, I'm going to just run through in a 2-minute thing. We were able to use the same kind of information to be able to predict some of the tribological properties, the friction, etc. And again, this ripples that I talked about earlier, they were pretty much influential in making those decisions. You don't even have to go to the microstructure level. You can, once you know the morphology, you can predict the tribological properties. Also, we were looking at using same acoustic emission to be able to predict hardness. We were kind of moderately successful, but the work is still going on. Right? So with that, I will conclude today's presentation. Again, I hope I was able to introduce you to this idea of autonomous materials discovery and manufacturing. And we talked about the smart hybrid machine system that we are working on, and the things that you can do with it. I mean, actually, what we have done is basically a minuscule amount of analysis of data that comes out of this. There is a lot more that could be done, and a lot more advancements we could do, both in terms of developing newer kinds of learning applications, as well as adaptation and control applications. On that note, I wish to conclude this presentation. Andy, thank you so much once again for inviting me. And everyone, thank you for being here. Thank you.